thank you for the nice presentation. Hello everyone, I'm Davide Biagini from Delft. And in the next 10 minutes, I'm gonna present some results and I'm gonna show you why, in my opinion, the current way we define fatigue growth in barely visible impact damage in composite should be changed. It doesn't work. So, first of all, my title ends with a question mark, and this is because I don't have an answer for that. But I have a couple of suggestions based on some experimental results that we obtained in our lab. So, yeah, and I'm gonna present this. So first of all, why do we care about impacts in composites? The one you see in the picture is a very small dent here. And if we obtain with a 34 joules impact, and as you can see, the depth of the dent is quite small, so it's 0.2 millimeter. So it's very difficult to see it with a naked eye. But if we then perform an ultrasound inspection, you'll see that there's a pretty large lamination underneath the impact dent, and this is not visible. So the question is, what happens in case, because these kind of impacts are quite common in aircrafts. So what happens, for example, in the case of an aeronautical application, if we have an impact case and we don't detect the impact damage and we continue to fly for a lot of time. So of course this regards the fatigue after impact. And the one you see here is, these are results from a paper from 20 years ago by Chen. And they monitor the propagation of the lamination width towards the life of the component. And as you can see, we have different phases, but at the beginning we see very little growth, followed by a very fast propagation close to the end. And this was a result that was observed in a number of work, and that's why we talk about an unstable and unpredictable growth in this case. And for those of you expert in certification aeronautical structure, this is also the reason why we use a no-growth procedure in design. But we don't see the actual damage. What we see here is a representation of damage that is provided by an inspection technology, which is the ultrasound inspection. And we know it has some limitations. So for example, we don't see the lamination, small delamination placed underneath larger one. So a growth like the one you see here would be shadowed, so we would not be able to detect this case. And there's a second limitation, so we only see the lamination, but other damage mode at a smaller scale, we are not able to see them, like matrix cracking, fiber matrix debonding, fiber failure. So the question is, what if we could detect all the damage? We would still see a curve like this, so with a small accumulation followed by a fast growth close to the end, or we would rather see a more progressive and gradual growth? And this is actually a very meaningful question, because the second case is much more desirable for damage-tolerant design. So to rephrase the question in a more scientific way, I think, we should rethink about we define growth, because the current definition is not based on the physics of growth, but is based on what we can and we cannot see in damage. So to investigate this, we perform a series of tests in our lab. So first we perform some impact tests with the impact tower, and then we perform some static and fatigue compression after impact tests. These are standard tests. You can find them in the ASTM standard. But what we did, we also performed some digital image correlation to capture the surface displacement. We used acoustic emission technology to monitor the acoustic activity. And we also perform ultrasound scan in a water tank scan we have in the lab. So first, I would like to present some results from the acoustic data. And these are regarding the static test. So the reason why we used acoustic is to separate damage modes. So it's an online passive technique. And if it's used in the proper way, it allows to separate damage modes as they appear, as they happen during the test. And to be comfortable with what we were seeing, we performed some simple tests where we knew in advance that some of the damage modes were happen in a predominant way. And Then we perform a continuum wavelet analysis, which is a nice technique that allows to analyze signals in time and frequency domain. And we were able to separate some of the damage modes. This is actually not trivial, and it's still it's not easy to separate damage mode in acoustic emission. But what you really need to remember from this is that we found some frequency separation between the damage modes. So considering this, then we perform our compression after impact static test. And as you can see, here you see plotted in the y-axis the weighted peak frequency. We found some cluster that we attributed to certain damage modes. And what we need to take out from this is that we have different damage modes active already from a relatively low stress. And this can be meaningful for fatigue. So we cannot a priori consider only one damage mode. We need to include more in our analysis. So it's not justified to exclude some of them a priori. And this regards the static test. Then for the fatigue instead, I would like to discuss a bit about our ultrasound scan results. So first of all, this is a C-scan after an impact, after a few cycles. And this is something is usually observed in the literature in case of an impact damage. So underneath the impact, there is an area with very small delamination is formed, because during the impact we have out-of-plane compression stress. So we observed that with the C-scan. So the question is, I told before that right now we only look at the damage width. So, but it's possible also probably to have propagation inside this area. So to test this hypothesis, we performed periodic C-scan while we were stopping the fatigue test. And this is actually what we observed. So before observing growth outside, we actually observed growth in the non-damaged cone. So, but then, of course, after that, maybe we start seeing delamination growing outwards of this area. And this is actually what we observed. So, and this led to failure eventually. So as a consideration, right now we only see the damage width. So in this case, if we only consider the damage width and not the propagation inside the damaged cone, we see that until the very end of fatigue, we don't see any growth. While if we include the normalized area, we see a much more progressive growth. So, but the question is, what if there are other possibilities to have growth, not just the damaged cone, to have growth shadowed by the C-scan, and there are also other possible damage modes that we could include. So the question is, if we could include other damage modes, then we would see still a growth much more progressive, or we still see a growth very close to the end. And to better answer this question, we have some future works where, so I showed acoustic emission data just in the case of static tests, but I'm currently busy with separating damage mode also in fatigue using acoustic emission, and that's quite tricky because there's much more noise and there are problems with that. And the second aspect, I've told you that there are other possible ways to have shadowed propagation of delamination. And to do that, we are developing a numerical model for 2D delamination propagation to see where the delamination could grow and if there are patterns. So concluding, I think the current definition is not based on physics, but on what we can and we cannot observe. But I think implementing these steps and focusing our attention on this, maybe we can have a better understanding. So thank you, and if you have questions.